To this point in the course, our discussions of multiparticle systems have largely focused on using the energy principle. However, it's also important to examine our other fundamental principle, Newton's second law, from a multiparticle system point of view too. Actually, anytime we've studied the motion of real-world objects like stars and people and such, using Newton's second law, we have, in fact, already been using a multiparticle form of Newton's second law in a quiet, implicit way. Today, and in the next few lectures, we're going to study this fundamental principle in its multiparticle form more explicitly. To do this, we're going to examine Newton's second law cast in the form that focuses on momentum. This form, as we know, is referred to as the momentum principle by the textbook. We'll see that momentum is a natural physical quantity to use when discussing multiparticle systems. To start, let's recall that for a multiparticle system, we know how to find the center of mass. If we multiply both sides of this expression by the total mass and differentiate both sides with respect to time, then we see that on the left-hand side of this expression we have a quantity with the dimensions of momentum, the product of the total mass times the velocity of the center of mass. On the right-hand side, we see each particle's mass multiplied by the particle's velocity, equivalently the momentum of each particle. The right-hand side is just the sum of the momenta of all the particles in the system. This tells us how to find the momentum of a multiparticle system, provided we know the momentum of each particle in the system. Now let's take a look at what we get if we differentiate this expression with respect to time. If we do that, then the left-hand side becomes the time rate of change of the system momentum, which looks like the beginnings of a multiparticle Newton's second law, or momentum principle. The right-hand side ends up being the sum of the time rates of change of the momentum for the particles in the system. We know how to apply the single particle momentum principle, Newton's second law, to each particle, which tells us that dp dt for each individual particle is just the sum of forces, the net force, on that particle. So using that here, we see that dp dt for the multiparticle system is just the sum of all the net forces on all the particles in the system. We might be tempted to stop here, but we can go a bit further. Let's say that the specific forces at play in this case look like this. Assume that each particle can interact with each other, and we'll assume here that those interactions are reciprocal and follow Newton's third law, like gravitational and electric interactions do, so that the interactions expressed as forces on different particles can be related. For example, the force on particle 1 due to particle 3, F on 1 due to 3, has the same magnitude as F on 3 due to 1 and is oppositely pointed. The same holds for the interactions between particles 1 and 2 and 2 and 3. In addition, let's assume each particle interacts with unseen agents in the surroundings. Here, for simplicity, we'll assume that there's one such interaction for each particle. Now let's go ahead and write down explicitly the sum of the forces on each particle. And then we'll add up all the forces on all the particles. Let's now group, where possible, all reciprocal pairs of forces that show up. We see that something pretty amazing happens. We see that every force that is exerted by one particle on another inside the system can be paired up. And by reciprocity, Newton's third law, these pairs of forces cancel, which means that the sum of all the forces on all the particles in the system boils down to just the sum of all external forces, all forces exerted on the multiparticle system by agents in the surroundings. In this particular case, there is only one external force on each particle. However, we can show that these results still hold even if multiple external forces act on each particle. So now we have arrived at our multiparticle Newton's second law expressed in terms of momentum, or equivalently, our multiparticle momentum principle. If the system momentum, the sums of all the momenta of the particles in the system, changes in time, then the time rate of change, dp system dt, is equal to the net external force, the sum of all the external forces acting on the multiparticle system. There are profound consequences that follow from the multiparticle form of this fundamental principle. First, if there are no external interactions, no net external forces, then F net external is 0. This means that dp system dt, the time rate of change of the system momentum, must be 0. In other words, the system momentum is not changing in time. It's constant in time. It has the same constant vector value. If this is true for our system, then we say the system momentum is conserved. Notice this is true even if the particles are pushing and pulling on each other, and individual particles in the system could be undergoing changes in their momentum. The overall system momentum can't change as long as the net external force is 0. Now, since we have the flexibility to choose what we call our system, we can often choose the system to include everything that interacts with each other, so that we end up with a situation where the system momentum is constant in time. As one extreme example, if we choose as our system the entire universe, namely there is nothing in the surroundings to interact with, then our fundamental principle tells us that the total system momentum of the universe, P universe, is a constant in time. However, to illustrate the power of momentum conservation in everyday life, we examine examples that don't require us to look at the whole universe at once. And we'll do that beginning with our next lecture.